Namaskar and welcome once again to another lecture in this course on Introduction to Infrastructure Asset Management, which is being offered by me and my colleague Professor Chirag Kothari. Today we are in module 7 and we will talk about chloride penetration in concrete and reinforcement corrosion. This is a normal warning which I have been giving you in all the lectures, that the material being used here is only for academic and instructional use in this course and should not be used for any other purpose. So far in this course, we have done an overview of the course content, including conduct and an overview of the infrastructure asset management. We have talked about schematic representation of deterioration and performance versus time curves, an examination of the concept of service life and maintenance action in that framework. We have talked about case studies highlighting the role of different stakeholders in different phases of the project and the importance of a comprehensive strategy towards infrastructure asset management. We have talked about decision making frameworks, including performance modeling considerations in budget allocation. In the last class, we talked about carbonation as a case study of actual deterioration process or mechanism, and we talked about how the penetration of carbon dioxide from the atmosphere into reinforced concrete structures affects these structures by way of the penetration of carbon dioxide and finally, the corrosion of these bars. We talked about the consumption of calcium hydroxide and the consequent reduction in pH in pore solution of concrete and the deposition of calcium carbonate and the subsequent corrosion. We have talked about this slide earlier, where we talked about basically the 5 mechanisms which have been identified over the last several decades, outlining the different important deterioration mechanisms: chloride induced corrosion, carbonation induced corrosion, alkali aggregate reaction, exposure to freezing and thawing, and chemical attack. And today our discussion is largely focused on chloride induced damage due to reinforcement corrosion in the general framework of the asset management that we have been talking about. As last time and throughout the course perhaps, an overdose of technical details has been avoided, keeping in mind the promise that this course focuses on management of infrastructure and technical details are included only to the extent that they facilitate better understanding of technical issues by non-technical asset managers. So, commencing our discussion, let us take a view of reinforced concrete. So, this is the reinforcement that is buried inside a concrete structure, whether it is a beam or a column or a slab, and we have this cover thickness which is either in this direction or in this direction or in this direction here. Similarly, the cover in this picture can be seen in these 3 directions, and that is the kind of protection to this reinforcing bar against any deleterious action or deleterious material which may be present on the surface of concrete. That deleterious material typically diffuses or penetrates into the concrete over a period of time. If we take a closer look at a neighborhood of this reinforcing bar as far as concrete is concerned, so we have concrete and we have steel. So, this steel bar is buried in concrete. Now, if we take a closer look at the concrete itself, that comprises aggregates and mortar and paste, which is shown here. Now, if we take a very close look at a very small element in the paste phase, what we find is this here is the hardened cement paste and we have pores, and these pores are basically contributing to the porosity of the matrix here and in the larger sense the porosity of the concrete around this reinforcing bar. This porosity, as we can see now, is directly related to the properties of the concrete that we have here. Parameters like water cement ratio, the cement type, the cement content, and so on. The curing that was carried out, the quality control that was exercised when constructing the structure, all these factors contribute to the pores and porosity in concrete, and that has a direct bearing on the durability of the concrete. So, moving forward, let us look at corrosion in general and the corrosion as it happens in the reinforcement in concrete. As far as corrosion in general is concerned, the principle of it involves the conversion of iron to its oxides and hydroxides in the presence of oxygen and water, as is schematically shown in this equation. Iron left in the atmosphere corrodes easily, and that is something which we all know and experience in daily life. However, corrosion of reinforcement in concrete is not so common, even though oxygen and water are both available in the concrete. So, this is what is shown here. We have the steel bar, we have concrete, and of course, I have called this part as cover concrete, which is slightly different from main concrete, even though usually it is the same concrete, except that for different reasons the properties of cover concrete are at times slightly different from that of the main body concrete. And why that is so, I am leaving it to you to think and study from the literature. Now, as far as the reinforcement or steel bars in concrete is concerned, there is a high pH environment, and that is the environment of these steel bars is concrete, and this concrete has a lot of calcium hydroxide, which leads to a very high pH in the pore solution, and this high pH environment leads to the formation of a dense passivating film of gum iron oxide, which acts as a passivating film on the surface of the steel bar. And now, so long as this film is intact, the iron surface is not open to the reaction with oxygen and water. So, this reaction of iron going to oxides and hydroxides can happen only if the surface of the steel bar here is exposed to oxygen and water. So long as this passivating film, which is shown here, is intact, this surface is not exposed to oxygen and water, and therefore, in general, very easily we do not see corrosion in the reinforcing bars embedded in concrete. However, once this passivating film is lost or damaged, then the reinforcement bars are rendered susceptible to corrosion, and that is what we see here. One case that we saw last time is carbonation, that is, as carbon dioxide penetrates into the cover concrete, the pH is gradually reduced, and once that pH reaches a level that the passivating film is no longer stable, we have an unstable protecting film, and therefore, the steel bar or this surface, as a matter of fact, is rendered susceptible to corrosion. The same mechanism in the case of chloride attack is slightly different, because the protecting film is damaged by the presence of chloride ions in the rebar neighborhood. That is, as chloride ions move into the cover concrete, they tend to damage this passivating film. Now, why they damage it, that is something which I would leave to you to understand, or why or how the chloride ions lead to this damage is something which we are not going into as far as this course is concerned, and those of you who are interested can obviously read up the literature. Having said that, in order that these chlorides attack and damage the passivating film, it is important that the chloride concentration here reaches a certain critical value. So, obviously, to begin with, we would expect that there are no chlorides in the neighborhood of the reinforcing bar. It is only over time and under certain conditions that chlorides will build up in this neighborhood, causing damage. So, that is the kind of discussion that we need to do when we talk about chloride induced reinforcement corrosion, which is the focus of our discussion today. However, before we go there, let me just spend a minute on the mechanism of corrosion in concrete. Now, corrosion is an electrochemical reaction, and how that electrochemical reaction proceeds in concrete is given here. Iron going to iron ions, liberation of electrons at the anode, which is here, and this is the area where the passivating film, which is represented here, has been damaged. So, at the damaged area we have iron being converted to iron ions and electrons being released, and these electrons flow through this steel bar, and at cathodic sites the oxygen and water is consumed in the presence of these electrons, and we have the formation of hydroxyl ions. So, in an overall reaction, iron and oxygen and water, they give you some kind of hydroxides and oxides of iron depending on a lot of other factors, and this is the overall corrosion mechanism. So, what is happening here is corrosion products are being formed, that is number 1, and iron is being consumed, that is we have metal loss, that is we have loss of metal as far as the anode is concerned, which in our terms translates to loss in cross sectional area of the reinforcing steel. So, basically corrosion currents are set up between the anode and the cathode, and concrete acts as an electrolyte in the corrosion process. So, this corrosion process is not complete unless this migration of hydroxyl ions formed here is complete and they move towards the anode, where they can combine with the iron ions being liberated here. So, basically concrete is acting as an electrolyte through which the hydroxyl ions move and the electrons move through the steel bar. So, this corrosion current being set up leads to consumption of the metal and formation of corrosion products, as I just said. So, basically the reinforcement corrosion leads to loss of metal and formation and deposition of corrosion products on the reinforcement. Now, as far as these products of reinforcement corrosion are concerned, it has been found that these corrosion products occupy a lot more volume than the parent iron. In other words, as this iron gets converted to these corrosion products, which are diagrammatically shown here, these products have a volume which is greater than the parent metal. And this is something which is very interesting and important from the point of view of reinforcement corrosion in concrete, because the formation and deposition of these corrosion products on the bars leads to the formation of longitudinal cracks. Now, how that happens is shown here, that is, this is steel bar here surrounded by concrete. Once these corrosion products start forming here, this leads to a situation where this system here can be broken up into this part and this part representing the steel and the corrosion products formed and deposited on the steel bar and the surrounding concrete. Now, given the fact that these rust products or the corrosion products, they occupy more volume than the parent metal, this concrete is subjected to expansive internal pressure, and by the same token the rust itself is subjected to compressive external stresses, or whatever you may call them. The fact of it remains that the formation and deposition of these corrosion products in the reinforcement, on the reinforcement in the concrete, leads to concrete being subjected to, and concrete being weak in tension, simply cracks. How that happens is shown here. We can see that on account of this radial expansive pressure, there is a stress buildup here which is tensile in nature, and concrete cracks. So, this crack is basically along the direction of the reinforcing bar, and depending on what kind of a member we are talking about, if it is a slab where these reinforcing bars are shown like this, we will have cracks which are shown here and other cracks which will propagate to some extent in the other direction. If we are looking at a corner it's possible that we'll have a crack something like this, or sometimes concrete will crack like this. So, there are different models or different ways in which the cracking in the cover concrete will happen. And once the cracking exceeds a certain amount or the corrosion exceeds a certain amount, then this concrete here can simply spall off. That is, it just comes off from the main structure. And we have a situation something like this, that these reinforcing bars here are exposed to the atmosphere. So, there was a cover concrete around them, which has over a period of time spalled off because the reinforcing bars corroded. Now, why they corroded? It could have been on account of carbonation or chloride penetration, but the formation and deposition of corrosion products on them led to this kind of spalling of concrete and deterioration. So, now going back to our focus for the day, which is chloride induced corrosion, let us spend a minute on what could be the sources of chloride for reinforced concrete structures. One could be just the construction materials. We know that concrete in principle comprises water, cement, sand and coarse aggregate. Other than that, we could have admixtures. Now, if any of these materials contains chlorides, that becomes an integral part of the concrete even when it is constructed. So, that is one source, that is in the construction material itself we had a certain amount of chlorides. It could come, for example, from sand if we use sea sand, or at times from admixtures, depending on what kind of admixtures we use. Some of them may contain some chlorides. Another source of chlorides, of course, is the marine environment, where the chlorides in seawater that attacks the concrete. Now, that can happen in different parts of the structure. We had talked about a situation where we had said that, okay, if we model a reinforced concrete marine structure in a manner that this part is always submerged in the ocean and this part is always exposed to the atmosphere, and we have a part which is cyclically exposed to seawater by way of either the tides or the splash. So, there is this situation where different parts of this reinforced concrete structure are exposed to chlorides on account of seawater, and the extent of attack and so on is different depending on what part of the structure we are talking about. Not only structures which are in the sea, also the structures away from the sea, that is structures which are away from the coastline. They are also subjected to marine environment in a certain sense of speaking, that is through the breeze. So, at times the winds or breeze that blows from the ocean towards the land carries with it a lot of chlorides, and those chlorides get deposited on the surface of concrete structures which could be inland. So, depending on the distance from the coastline, structures could be subjected to different levels of chloride attack again. Another possibility of chlorides attacking the reinforced concrete structures arises in the case of use of de-icing salts. Now, this happens in cold climates where there is a lot of snowfall, and in order to melt away the snow that collects on highways, we sometimes use de-icing salts which are chloride rich, and that salt through the dissolution in water lands up on the tires of vehicles, and these vehicles take it to garages and other concrete structures. So, these structures are then susceptible to chloride induced reinforcement corrosion. So, there are different types of structures which are susceptible to or vulnerable to chloride induced reinforcement corrosion depending on the source of chlorides. So, now how is this penetration of chloride ions modeled as far as engineering is concerned? So, what we are looking at is chlorides at the surface of this kind of a concrete structure, and we are trying to better understand how to model the movement of chlorides into this concrete. We know that reinforcing bars are placed at a certain distance away from the surface, that is what is shown here, and that is what is called cover. So, in this diagram we say that okay, this is my concrete, this is the environment, and we have a certain amount of chloride concentration here, let us say, and the reinforcing bars are placed at a certain distance away from the surface. And this figure shows an intuitive progressive ingress of chlorides into the concrete with time. So, what is shown here is that if we assume that the surface concentration of the chlorides remains constant, then over a period of time gradually the chloride concentration within concrete will follow the profiles which are shown here. So, this is the earliest, followed by this, followed by this. Obviously, it will not be such a neat looking variation, there will be some problems which we will talk about later. So, in principle what is being stated is that over a period of time, for a given chloride concentration, the depth which is compromised will keep increasing. Now, that said, what we have to ensure really is that the chloride concentration near the bar should not be allowed to exceed the critical level within the service life of the structure. So, this is the important bottom line, that is, within the service life of the structure we must make sure that the chloride concentration in the neighborhood of the bar does not exceed a critical level such that the corrosion can be induced. So, that becomes the guiding principle as far as design is concerned at the first instance, and as far as the management of that infrastructure facility is concerned in the management phase. So, of course, what we have assumed here is that the surface chloride concentration is constant. Now, these are the kind of things which we need to discuss, and we will probably talk about it briefly towards the end of this lecture today. Mathematically speaking, this penetration of chloride ions into concrete is modeled as a concentration gradient driven diffusion process given by this differential equation, whose solution is this. Without going into the details of this mathematical formulation, let us try to understand only the engineering part of it. This equation here is the solution of the differential equation that we talked about. So, basically what we have is a representation of what will be the concentration of chlorides at a given depth x from the surface after a time t of exposure. So, this is the Cxt, this is the time of exposure, and this is the depth from the surface. Remember that we are talking of penetration of chlorides through these pore spaces, and this concentration that we talk about here is in the same units as this C0, which has been treated as constant. Also, this d represents the ease of movement of chlorides through this concrete. That is, this d is largely determined by the properties of the concrete that we are talking about. Now, once we go to the actual structure, this equation represents what is the concentration of chlorides at different depths at different points in time. Now, as I mentioned, the d represents the ease of diffusion and depends on the porosity of the concrete matrix, that is water cement ratio, cement content and cement type and so on, and factors such as the level of saturation of the pores. Obviously, in a concrete that is completely dry, we do not expect any diffusion of chlorides to happen, but if it is completely wet all the time, then the movement of chloride ions is largely facilitated. So, basically, as far as the durability design is concerned, we are talking of three critical parameters. One is the surface chloride concentration, and the second is the coefficient of diffusion of chlorides in the concrete, and third is the critical chloride concentration for the onset of corrosion. Now, each of these depends on a large amount of factors, including the exposure conditions. We spent some time today discussing the different exposure conditions that are experienced by structures susceptible to chloride induced damage. The de-icing salts, the marine environment at different components, the submerged, atmospheric or the tidal zones, and they will require different kinds of mathematical models for the surface chloride concentration or the coefficient of diffusion, but that is something which we will not go into as far as this course is concerned. We will stick to a simple understanding that okay, if this kind of a model is largely accepted as far as the profession is concerned, then what are the steps that we need to take as far as design of structures which are vulnerable to chloride induced damage is concerned, and where we periodically collect data through inspections. So, now relating the diffusion coefficient to parameters such as the water cement ratio, this is the kind of data that we have from published material. So, we find that there is a lot of variations, but this data gives a direction to research that well, for ordinary Portland cement or for blast furnace cement, there is a variation in terms of how the diffusion coefficient changes with the water cement ratio. So, as a thumb rule or to begin with, if nothing else is available, we can use some of this data to estimate the kind of diffusion coefficient that we are likely to experience for a given concrete, where the water cement ratio and the cement type etc. are known. So, based on that estimate of the diffusion coefficient, we can carry out a preliminary analysis, and that can be validated over a period of time through periodic inspections and data collection, as we shall see in another lecture. Similarly, as far as the surface chloride concentration or C0 is concerned, the Japan Society of Civil Engineers has proposed the following values, which is in kgs per cubic meter and can be used for different conditions. For tidal and splash zone, it would be 13, for the coastline it would be 9, and depending on the distance from the coastline, it could be varying from 1.5 to 4.5 and so on and so forth. So, now these are only values till such time as better estimates or approximations become available. Now, as far as the third critical parameter is concerned, that is the critical chloride concentration for onset of corrosion. This is a very important parameter because chlorides will penetrate into the concrete anyway. What we have to only ensure that the cover is sufficient to the extent that in the surface life of the structure, the concentration in the neighborhood of the bars does not exceed this number. So, as far as this parameter is concerned, the Japan Society of Civil Engineers endorses a value of 1.2 kgs per cubic meter, which could be revised again once more or better estimates are available. Estimates ranging from 0.3 to 0.6 and 1.2 to 2.4 are available in different literature that we see. Now, that is where the science and engineering is different. This is a lot of evidence which has happened from different conditions. For example, these values have been reported in accelerated tests. These values are from realistic environments. So, basically the JSCE has given a guideline of 1.2 and has made it open to the engineers to collect more data and refine this critical parameter. So, moving forward, how do we design against chloride induced reinforcement corrosion? We simply ensure that the concentration of chlorides at a depth L at a point T, where T is the service life, this value should be less than the critical chloride concentration, and that can be achieved through a combination of the cover length L and the diffusion coefficient D. Now, this diffusion coefficient can be controlled by controlling parameters like the water cement ratio, cement content and so on, and this of course can always be controlled. So, basically we can control the properties of this matrix and the depth of this matrix. Once we do those two things and ensure that the chloride concentration at the location of the reinforcing bars does not exceed the critical chloride concentration during the service life of the structure. Now, if the service life of the structure obviously becomes very large, we need to have a reasonably large L and or a very small diffusion coefficient. So, that exactly is the challenge for durability design. If we compare this discussion with what we did for carbonation, it is almost the same thing. So, in carbonation what we tried to say was that if this is the cover concrete, the cover provided should be such that it exceeds the expected depth of carbonation. So, this expected depth of carbonation D is exactly the depth that we know will get carbonated or is likely to get carbonated for a given level of diffusivity of carbon dioxide in this case over a period of time t. And this, if you recall, we said that as far as the carbonation discussion is concerned, the depth of carbonation D is basically related to the root of time. So, this K is more or less like the diffusion coefficient here, and this represents the ease through which carbon dioxide moves into the concrete, and this is a gross simplification and a slightly different representation of the equation that we just used as far as chloride penetration is concerned. All that we have done here is that we have added a further disclaimer or a factor of safety, if you want to call it, of x millimeters. That is, we said that the cover depth should be D plus x. So, basically what we are saying is that we do not want the depth of carbonation to reach exactly C. We want the depth of carbonation at the end of service life to stop at x millimeters away from the reinforcing bar. We can have the same discussion in the case of chloride induced reinforcement corrosion and say that what we need to ensure is that the chloride concentration at a depth D should be less than the critical concentration, and once we know this depth D, we should provide a cover which is basically this D plus Nx. So, this is largely the similarity between chloride based approaching carbonation induced corrosion and chloride induced reinforcement corrosion in concrete structures. So, with this we come to an end of our discussion, and this slide gives you the references and some suggested reading to help you understand the subject matter better. And I would like to conclude the lecture by expressing my thanks to my teachers, colleagues and students over the last several decades who have contributed tremendously to my understanding of infrastructure creation and maintenance. Thank you.